Hi everyone. In today's video, we will be discussing how big is the universe in which we live, and from so many perspective, it's a very important question. So, we will be discussing. Uh, how big is the universe according to science, and how and why people believe that the universe should be so big. So let's just start. So uh, the outline is very simple. We will be discussing first about astronomical units that we usually use to measure the distances in the universe. And secondly, we will discuss about the distance measurements methods in the universe, like how we uh, calculate that how far is a certain galaxy from us in the Milky Way. So, and then we will, for sake of the comparison, we will see how everything in this universe uh, compare can be compared to each other in terms of the length scale, and we will see that the universe consists of very small particles up to the very big objects like the galaxies and the galaxy structures and the universe itself. Well, universe itself is an object. And in the last, we will be discussing how big is the universe and why. So we begin. So astronomical units in science, if you know the basic science, you know that all the quantities need to be measured in some units. For example, a kilogram is a unit of mass. Similarly, the meter is a unit of length. When we say the distance, it actually means a length. And then the time, the unit of time, the smallest unit of time is second that we use in science, but obviously there are other big units like the minutes or hours or years. So one of the main important, if a quantity in the universe, is the distance, because we are dealing here with these questions that how big is the universe. So the distances are usually of two types. Okay, so before I move to the distances, so you know that the basic quantities in the science are only three. It's the mass, length, and time. These are the fundamental quantities in the nature that needs to be measured if we want to specify and quantize some kind of an amount in the sense of mass, length, or time. So MLT just means mass, length, and time. So obviously there are other quantities as well, but those are mostly derived from these three quantities. So we call that the mass, length, and time are the fundamental quantities in science. Okay, so back to the distances. So the distances are usually in two types. So one is the linear distance, and we know that the linear distance is usually measured in the meters. But in astronomy, we use the bigger units. they are usually called the parsec or the light year. We will briefly describe them a bit later soon. Okay, the second type of distance is the angular distance. So angular distance, you know the angle, right? So angle is always measured in the degrees. So the degree is actually a kind of distance, but in the angular sense. So, and obviously the smaller units of from the degrees are arc minute and arc second. It's just like that in 1 hour you have 60 minute, and in each minute you have 60 second. Same is in case of the angular or distance. You have the degree, and in 1 degree you have 36 arc minutes, and in 1 arc minute you have 30 in 1 degree you have 60 arc minute, and in each arc minute you have 60 arc second. So the arc second is a very very small angle. Even 1 over 36 hundredth fraction, I mean 3600th fraction of a degree. So it's a very small angle. Okay, the mass, we usually on Earth we measure the mass in the kilograms, or the smaller unit is the gram. But in astronomy, because the objects are so massive, like this Earth, the Sun, so if we describe them in the kilograms, it will be very large numbers. So we introduce another unit called solar mass. So, and the time is usually always used in the seconds, because for some reason we always use the second. So before we move to describing the units, keep in mind that the physical changes in the universe happen over a very long time, much higher than the human lifetime. So the period of the time period over which the physical changes appear in the world is order of a million to a billion years. So sometimes it's a problem, because that really means that you cannot see things happening in the real time, of course, but this is just the way nature works. So so back to the distances. So the first unit is called astronomical unit. For some reason, very obvious reason, if we want to study the planetary system, then it's good to use this unit. And the astronomical unit just means that the distance between the Earth and the Sun. So the distance between our Earth and our Sun is called 1 astronomical unit. And if we describe in meters, it's about 1.5 10 to the raised power 11 meters. So let's say it's about 100 billion meters. So the light from the Earth is the Sun from the Earth is about 100 billion meters far. So, or you can say that the Sun from the Earth is 1 astronomical unit away. So if the Sun from Earth is or if the Earth from the Sun is 1 astronomical unit away, then the Mars is even further. So Mars is 1.52, almost 1.5 astronomical unit. And then we have the bigger units called, actually very big units, called the light year. The light year is the distance that light can travel in 1 year. This is how we describe the light year. So it's very easy to calculate. So you know the speed of light, and you know that the speed is distance over time, and the time is 1 year, and you can convert 1 year to the seconds, and you can just calculate how much distance. So in light years, so 1 light year is equal to almost 9.5 10 to the raised power 15 meters. It's a very high number. So it means that light can nearly travel 1 million of a billion meters in 1 year. So that's very huge. And then we have some other units specifically very commonly used in astronomical studies, and I will later explain you why. This unit is called parsec. So the parsec is that if one astronomical unit length makes 1 arc second angle at some distance, then that distance is 1 parsec. So suppose you have here you have the earth, and here you have the sun. So this length we know is 1 astronomical unit, and we go far from this point, keep going till a place that this length makes a very small angle equal to 1 arc second. So this angle is very small, it's 1 arc second. So then this or distance, like this one or this line, this or distance is called 1 parsec. And if we calculate, it has to be 3.086 multiplied by 10 to the power 16 meter. So you see it's even bigger than the light year. So the light year is order of 10 to the power 15 meters, and the parsecs is of order of 10 to the power 16. Although they are almost comparable, not too much, because this is almost 9.5. Okay, and the mass in astronomical objects, in stars or the galaxies, we often measure in the units of solar mass. So solar mass is just nothing, just the mass of our sun is called one's solar mass. So our sun's mass is about 10 to the power 30 kilogram. 2 multiplied by 10 to the power 30 kilogram. So you see this is a very huge number. 10 to the power 30. This is just mass of one sun. And could you imagine how much would be the mass of a galaxy then? Because a galaxy has about 2 to 300 billion stars which look like our sun. So it would be a huge number. So we can just reduce the number by introducing this unit. So rather than saying that the sun's mass is 10 to the power 30 kilogram, we can just say that the mass of our sun is just one solar mass. By the way, a mass of a black hole in the center of a galaxy could be from 1 million to 1 billion masses of sun. So this 10 to the power 6 is 1 million, and 10 to the power 9 is 1 billion. Okay, so the next question is that, okay, these are very big numbers in meters. So how do we know how much far away a star or a galaxy is from us? So there are lots of methods to find out the distance of a given star from the Earth. Of course, you won't be using the meter tapes, right? Because you can't really make such a long meter tape on Earth, and then even if you make it, you can't take it to that star. So you have to find some other ways. And just an example, the nearby galaxy to Milky Way is Andromeda, and Andromeda is 2.5 million light years away from the Earth. So it means that even if you go from the light speed, even if you travel from the light speed from the Milky Way, you will reach in the Andromeda after 2.5 million years. So okay, so we are discussing the methods how to determine the distance of stars or galaxies, and the first very simple method is called the stellar parallax method. So the word parallax, it has a meaning which probably I don't know how to just explain it in the simple words, but you will get the idea here that suppose that there is stars here in the universe and you are here in the solar system. So this blue is Earth, and this in the center it's revolving around the sun. So this yellow is the sun. This yellow is the sun, and from here there is a, okay, let's say there is a star here very far away from the Earth, our solar system. So how we can find how much far away it is from the Earth? So so this method actually uses the Earth's rotation around the sun. So we know that the Earth completes one orbit around the sun in 1 year. So suppose that in June you measure this, you see that this star is along here. Okay, you see that this star is in this direction, and you measure how much angle it can make from the, okay, let's not talk about the angle here. You see that this direction is here, and 6 months later in December you are moved here, right, opposite to where you were in June. So then you see that the same star, if you want to see now, then the direction is along in this direction. So you can measure this angle. Okay, just half angle if I call, or let's call it P. Now this distance is D. Okay, let's just call it D. Okay, so if this half angle is P, then the formula is that then the distance, because we know that this is a triangle, right? So solving the triangle, we can find this relation that the distance in the parsec is given by 1 or divided by angle in the arcsec. So now probably you understand why we used the parsec as a unit, because whenever the angle is in the arcsecond, we get answer in the parsec. So to calculate the distances from the parallax, we introduced another unit called the parsec. So this method is very useful, and it was initially used for a very long time to calculate the distance to the nearby stars in the Milky Way, or not so far away, because if you keep moving, if the star is very far away from you, you will find that actually it will show no parallax. That even if you are in the June or you are in December, there is not much angle that you can measure. So this phenomena only happens when the objects are close to the Earth. But still, I mean, very far away. So usually the limit is about 1000 parsec, which still is a very huge number. So since this is a very accurate method, so it can also be used For the calibration of other methods of distance formation, we will discuss those methods in later. So just for example, the nearest star from to us is the Proxima Centauri. So the Proxima Centauri, if we measure its parallax, so the parallax angle P is just 0.768 arc second. So if we just use this equation, then the answer we get, d, the distance, is 1.3 parsec, or in the light years it's 4.25 light years, something like this. So okay, let's just call it's just 1 parsec away from us, almost. And some telescopes also use this technique. For example, Gaia Space Telescope, which recently released a lot of data. It used the parallax to determine the distance to billions of stars in the Milky Way and also beyond. So, and it can also exceed the limit of 1000 parsec limit that we can usually do it here from Earth. Keep in mind, from Earth it's not easy always to measure parallax, because atmospheric conditions also affect observations. So it's better to do from space telescopes. Okay, the second method, which is very common for large distance objects, to measure their distance of those objects which are those stars which are very far away from Earth. That method is called the standard candle method. Now the candle, you know what is a candle, right? So the standard candle mean, if you know a candle very well, you can use it as a standard a candle. And actually, the main core idea behind this method, of course, there are so many types of candles. We will briefly be discussing them. But the main idea that uses this method is that it uses the relationship between the luminosity and the flux. Luminosity and the flux to measure the distances. Okay. So you see here this equation that F is equal to L over 4 pi d square. 4 pi is just a constant, and F is the flux, and the L is the luminosity. So what does these two terms mean, the flux and luminosity? So the luminosity is the intrinsic brightness of a star, and the flux is the measured brightness that you actually you measure through a telescope. That's called the flux. And if you see that there is a inverse law, inverse square law. So this d is power 2, but it's inverse because it's in the denominator. So this equation is usually called the inverse square law, because the light follows inverse square law. Okay, I give you a brief example. So suppose you have two light bulbs. One is 100 watt and one is 500 watt. And you are outside in the dark night, and you see that these are two bulbs. The 100 watt is close to you and the 500 watt is very far away from you. You will find out that they both almost look equally bright. Okay, why? Because the 100 watt, even if its power is just 100 watt, but it's close to you, so it's still bright. And the 500 watt bulb, even though it's very far away from you, but its power is very high. It's in the 500. So according to the first bulb 100 watt, it has a smaller d, and the far away bulb 500, it has higher L. So both of these effects, they almost give you the same answer when you calculate for the two. So what I mean to say that if a star is very bright, it could have two meaning. Either the star is actually not very bright itself, but it's very close to you, or the star is very far away, but then it's extremely bright. So it could have these two meanings. So if you understand this, then we can move to the candles. So the first candle that we used is called the Cepheid variables. They are actually the pulsating stars whose light just follow kind of a wave, and because they follow a wave, so basically you can calculate the pulsation period, like the time period of the pulse, and there is a specific relation that relates the period and the brightness, or let's say the luminosity in this case. So for example, here you see this figure on the right side. So suppose that this is a spectrum of a star, and this is its pulse time period. So on x-axis you have seen that this first peak, it started as day 3, and the second peak is it comes at day 9. So this period is 6 days. So now you know that this star has 6 days of pulse period. So it means that it should have a specific luminosity, because its period is related to the luminosity according to this relationship. Now, so if you calculate the P, you can calculate the M, the brightness, or it's actually related to L. So you can calculate the L. So L you can calculate from this relation, and then you go back to this inverse square law. And from the inverse square law, you calculate F from the telescope, you found L from the period, and then you can just calculate the third unknown parameter here, that's the distance. So this is one way to find the distance, and this method works up to some million parsecs away from us. It's still quite large distance. So this is one. So one type of the candles we have is this variable stars called Cepheid variables, and the second type of candles that we can use to measure the distance is the supernova. So you know the supernova is actually called explosion of a star, right? There are various types of supernovae, and so the type 1A, a kind of supernovae, is actually used for as a candle. So what happens in this case, that so you should understand that a lot of stars in our universe, even in the Milky Way, they are not living as a single star. They are usually part of a binary star system, or even multiple stars which are rotating around a common center of mass. So suppose that you have a binary star, and one of them is a dwarf star. I will explain you in another lecture what are these stars. These are small stars basically, which are not very powerful, and what it does, that the dwarf star in a binary system, it can take the mass from the other star. It can eat, or the proper word is accrete. So it will accrete from its companion up to the mass limit of 1.4 solar masses. So it can eat more mass, as much as that its mass can become 1.4 times of the mass of our sun. And then what happens? Then it just explodes. So because it explodes at a certain mass, so each type of supernovae happening anywhere in the universe will have a constant luminosity L. It means that if you find a type 1 supernovae anywhere in the world, you know how much intrinsic brightness it has. Then what you do, you go back to this inverse square law, this first equation. You already know the L, and this F, the flux, you measure by the telescope. And then the third unknown from the equation, the distance you can calculate. So the D can be calculated. Now this is very interesting because supernovae are usually so bright that you can see them on almost near the edge of the universe because they are extremely bright when they explode. So it means that on the very large distances, supernovae can be used as a standard candle to find the distance to that galaxy in which it's happening. So the best, so how we measure the distance to a galaxy? Basically, we measure the distance to a star in that galaxy, and we approximate that, okay, if this star is this much far away, then this galaxy in which it is living, it's also this much far away, approximately. So it can actually very large distances up to the gigaparsec, or giga means billion. So the billion parsecs, which is actually order of the scale of universe. So I mean the observable universe. So it means that these two, this method especially with the supernovae, you can find the distances in the universe. So now since we have discussed how we find the distances, we can talk about okay, before we move next, there is another method commonly used, that's called the redshift. So we know that when a galaxy is moving away or a star is moving away from us, the light, which is initially white light or blue light, it becomes red. It becomes low energy because the space is expanding. What happens actually, if you see in this figure, the wavelength, this wavelength, it get stretched out. So this wavelength actually get stretched out, so the wavelength becomes long, so the energy becomes low because they are always opposite to each other. So when the wavelength becomes higher, the energy becomes low. So when energy becomes low, the blue light turns to red because the red is low energy than the blue. So this phenomenon is called redshift. So we use the Hubble's law basically. So in the previous video we discussed that the universe is expanding. So these galaxies which are moving away from us, they are moving with some specific speed v, which is related to the distance as this relation. This is called Hubble's law, that the recession speed is equal to the Hubble's constant multiplied by the distance of that galaxy. And redshift is a parameter that we calculate by observations. So suppose if a photon was emitted from the galaxy, if I know what was the wavelength when it was emitted, if I know that, and then I can observe the wavelength through the telescope, then I can, according to this relation, I can calculate the redshift. So here the lambda is the initial wavelength when the photon was emitted, and this lambda O is the observed wavelength. So according to this relation we can find the redshift. So now once we find the redshift can be converted to the recession speed using this relation V is equal to redshift multiplied by C, where C is the speed of light. So it means that once you know V, you can just put it in back to the Hubble's law here. And this Hubble constant you already know. Now you already know the recession speed v, so you can calculate the d, which is the distance to that galaxy. So that's also one way, and it can work to very high long or distance away. Okay, so these are some typical methods which are used to calculate how far away is a galaxy from us. But of course there are many other methods which are used in science these days. Okay, now we briefly compare the length scale in the universe, how small, from the smallest things in the universe to the largest ones. So what is the smallest thing okay, so suppose here, okay, here you are a human, and your size is about 10 to the power 0, which is 1. Okay, so this x-axis along this is in the meters. So humans are about 1 meter or 2 meter of length. So our length is about 1 to 2 meters, let's say, order of meters. And then there are mountains which are 10 to power 4 meters, let's say, order of kilometers. And then you have the sun. Okay, before the sun there should be an earth here, because earth is smaller than the sun. And then there is a sun which is a 10 to the power 9 meters size of the sun. And then you have the solar system, which is 10 to power 14 meters. And then you have a whole Milky Way, our galaxy, which is about 10 to power 21 meters. Well, that's a ridiculously large number. And then the whole universe itself, which is 10 to the power 26 meters, this observable universe that we can observe. Okay, these are on the positive side, on the higher side. How about the lower side from the humans? So from the humans, if you go to the smaller side, what is smaller than us? Of course, atoms. Okay, and okay, first maybe the grain of a sand, which is about 10 millimeter, 10 to power 4 meters. And then atom, which is a 10 to power minus 10 meters. Then the nucleus is even smaller, 10 to power minus 15 meters. And then you keep going slow, you will find protons, the size of proton or neutron. So what's the limit? So the limit is called the Planck's limit. So the Planck limit is actually the smallest length scale, the smallest length that you can measure in the universe. You can't measure things below the Planck's length. And what is that? 10 to the power minus 35 meters. Now this is very small number, ridiculously small. It's almost zero. So you are basically trying to measure the size of an object which is almost zero in size. So can you just imagine? So there is this question that why we cannot measure beyond this, even smaller than this. There are so many arguments why. So first, the main argument is actually the concept of space and time itself break down below this limit. So how this limit has been derived? This limit actually comes from the Einstein's theory of general relativity. So you find out that at this much small distance, the space cannot be described anymore. So basically it's all because it's almost zero. And then there is another argument. So suppose that this energy and the wavelength, okay, if you are using light to measure something, so you understand that this relationship, that the energy is inversely proportional to the wavelength of light. So if the wavelength of light is of order of this Planck's length, is a very small number, then it means you need very high energy. Now, if you have this much high energy in some space, it will not collapse into a black hole, basically. You can call it a microscopic in a black hole. So it means that physically speaking, it's not that theoretically this is unachievable, it's also that the physically it's unachievable. And then there is one limit, one reason that from the point of view of quantum mechanics, that at this much small scales, the space and time actually do not appear to be space and time space anymore. It basically you are dealing with the quantum field. So this is a fluctuating field, and when it's like this in the fluctuating fields where the word length loses its meaning. So yeah, so it means that this is the smallest number, the smallest size that we can measure in the universe. But keep in mind that does not mean that the space itself is made of some Planck or length-sized pixels of field or energy, whatever you call. It just means that that you cannot observe beyond that. Okay, so we move to the big questions now. That how big is the universe? That was our main question. So we turn to this question now. So we know that the universe is 13.8 billion billion years old. Okay, and we know that the universe is expanding. And usually people think that nothing in the universe can travel that faster than the speed of light. Now, if you assume that the space just expands with the speed of light, then it's very simple to calculate the size of universe. That after if the universe was made 30.8 billion light years ago, so it means that the size of the universe today should be 13.8 billion light years. Okay, this is very simple, right? Because what I'm asking here is that suppose here is a certain a flash of light, and the light just emerged and getting scattered in the universe, and then I know that this flash happened in 13.8 billion years ago. So if this light is traveling and the space can only expand as much as the light is traveling, so what should be the size of universe today? It should be 13.8 billion light years. Very simple argument. But the question is it? Is the universe really 13.8 billion light years ago? Okay, the simple answer is no. The universe is way more bigger than the 13.8 billion light years ago. It's bigger. And then you will ask me this question, okay, how big? When this is a tricky question, how big the universe is. Because it depends on what do you mean by universe. If you are okay, I can give you a simple answer. I can't tell you how big the universe is. I can only tell you how far you can see. So how far you are able to see, that's your edge of the universe. So let's just call it observable universe. Yeah, that we can actually measure, that how far we can see in the universe. So for all practical reasons, that is our universe. Is there something far beyond that? We will discuss it later. But here we are considering ourselves with the fish in the pool. So if you are a fish in the pool, you think that the pool is the universe, right? That the pool is the world, because for you that's the case. You are confined in the pool. You can only see the edges of the pool, so you think that the pool is the universe. So in the same sense, we can only see as far as we can see, and that we can say for the practical reasons that this is our universe. Beyond that, there might be universe, but we won't be able to see that. So let's just move to this debate. So the correct answer is that the observable universe is 93 billion light years in size. This is the diameter of the bubble. And there is another thing, it's called cosmological principle, that the universe is homogeneous and isotropic. So it means that wherever you are in the center of the universe. No matter you are in the Milky Way or you are in a far away in some other galaxy, you are always in the center of the universe, because the universe, everywhere you look around, it looks homogeneous and it's isotropic. It's everywhere same. It looks almost same everywhere, no matter wherever you go, because we are dealing with the very large distances. That's why. So it means that the radius around you is 46.5 billion light years. So if you are inside in the center of the bubble, so the each side of the edge of the bubble is 46.5 billion light years from where you are. So it means that on one side you can only see to 46.5 billion light years. So 46.5 on one side and 46.5 on the opposite side, so it makes 93. So that's the size or the diameter of the bubble or the universe. Okay, let's call it observable universe. So this argument that why not universe is just 13.8 billion light years, because as I told you, it was only the case if the universe was not expanding or the space was expanding with the speed of light. So what does this tells you? That universe is bigger than the expansion allowed by the speed of light. It means that somewhere in the past universe has expanded with the speed which is much higher than the speed of light, right? That's why the universe is not 13.8 but 93 billion light years. It's a huge difference, almost 80 billion light years higher than the in case of a speed of light expansion. So this is the reason that the space itself does not has to stretch itself by the speed of light. There is no limit to it. Try to understand it with an example of a slowly moving ant on a stretching rubber band. So if you are an ant and if you are moving on a rubber band which is it's stretching very fast, so what are the implications? That even if you are moving slow, in small time you will cover so much distance, because where you are walking, that band is actually in stretching, right? But if the band is not stretching, you will just cover very small distance. So this is how universe expanded to, because when the light was moving away from this Big Bang flash, so the space expanded and it just carried that light with that. So yeah. Scientifically speaking, if you want to solve the case and find this answer, because people will ask how this answer 93 billion light years was found. So you have to solve the Friedman, Robertson, Walker metric. So this is basically an equation that tells you what is the distance between 2 points in the universe. But then you can only solve the case if you have to assume a cosmological model, and the current cosmological model is a flat universe. So assuming that the universe is flat, so you can solve this metric for light. Assuming a flat universe, you will solve the metric for light, and you will find that in 13.8 billion light years, the light can actually go up to 93 billion light years. So it means that the half of that is on one side. So 46.5 billion light years is as much as far you can see from Earth in any given direction. Now, this should be clear that no matter in which direction you are looking from the Earth, you can only see as far as 46.5 billion light years. Now, does that mean that there is no universe beyond that? No, no one has ever said that, but no one knows for sure. But there are some possibilities that would tell us that actually there is a universe. It's very convincing case. Why? Because the geometry of space itself is flat, and the flat universe is consistent with infinite size. So it means so the universe do not seem to have a curvature. Okay, I will not try to explain in terms of equation here. Just I tell you that if the curvature is 0, it means that something is flat. So the space looks very flat, and that really makes the scientists believe that that the universe could be infinite, although you can never say for sure. So this is the argument. So is universe finite? There is a probable answer, that is yes. Exact answer, no one knows. So this is what we can say. So the conclusion of the discussion is that yes, universe is probably infinite, but wherever you go, you take that 39 billion light years around you. So your universe will always be 46.5 billion light years in one side. So that was the overview. But trust me, these are not small numbers. So even if you are here on the Milky Way, in the Milky Way, on the Earth, and you want to go to the edge of the universe, okay, now suppose you have found a spaceship, you have made a spaceship that can move with the speed of light. You still need 46.5 billion years. Even if your spaceship can move with the speed of light, you needs 46.5 billion years. It's billion years, so it's a very huge number. So I suppose we have discussed a lot on this topic. So in the last, I just want to give you a map of the local universe. This is from the 2 mass redshift survey, and this is about 43,000 galaxies given in the 380 million light years from Earth. So it's just very small. It's just a 380 million light years from Earth, but you still see that there are so many galaxies here, right, in this local universe around us. and here it's given in the different colors. So the blue or the purple means that these galaxies are close to us, and the red ones means that they are very far from to us, and these other colors mean that they are in between. So guess what, this is universe looks like only within 380 million light years from Earth. So could you imagine how much fuzzy this image will get if we are making a map from Earth to the 46.5 billion years around the Earth. So yeah, so okay, that was the topic for today. I hope this was interesting, although there still remains a conclusion that is the universe infinite or not. But as I discussed, I think the key point was here that for our perspective, it's not an interesting question, because our universe, for us, the universe will always be 46.5 billion light years in a given direction. That's it. See you in another video. Okay, bye bye.